For over 1,000 years, one of the most important wind currents on the entire planet has followed a pattern predictable enough that scientists could reconstruct its behavior using nothing but ice buried in Greenland. Layer after layer, century after century, that ice recorded a story consistent enough that researchers trusted it to reveal exactly how this current had moved through time and exactly what a warming world should do to it going forward. The prediction was clear. As the planet heated up, this current should drift steadily northward. That's what the model said. That's what over 1,000 years of frozen evidence said. And then, in the middle of a summer marked by some of the most punishing, most geographically scattered heat waves in recent memory, scientists discovered the current wasn't going north at all. It was moving the wrong way entirely, and nobody had expected it. Subscribe to the channel before we get into this, because this is exactly the kind of scientific mystery I love uncovering. The ones where the evidence contradicts the prediction, and the real story is in figuring out why. Let's start with the mystery itself, because understanding exactly what scientists expected before we get to what they actually found is the entire key to understanding why this discovery genuinely surprised them. The jet stream, a fast-moving river of air circling the northern hemisphere 5 to 10 kilometers above the ground, exists because of a temperature contrast, cold air sitting over the Arctic, warmer air sitting closer to the tropics. That contrast is what gives the jet stream its speed and its shape. And researchers have spent years building an increasingly confident picture of how it should respond as the planet continues warming. Back in 2021, a team led by University of Arizona geoscientist Matthew Osman used something genuinely remarkable to test that picture: water isotopes, preserved in ice cores. Drilled deep into the Greenland ice sheet, layers of frozen evidence stretching back to the 8th century. By analyzing those isotopes, Osman's team reconstructed nearly 13 centuries of North Atlantic jet stream behavior, and what they found was reassuring in its own way. The jet stream's historical variations matched what natural climate fluctuations alone would predict, even accounting for the dramatic warming of recent decades. But their models projected something specific for the future, that under continued unchecked warming, the jet stream would undergo a progressive migration northward, one substantial enough that by around 2060, its behavior would become genuinely distinct from anything natural variability alone could explain. That was the expectation. A slow, steady, predictable drift toward the pole, tracking the broader warming of the planet the same way you'd expect nearly every major wind system on Earth to eventually respond to a warming atmosphere. And for a while, that expectation held. Then came 2026. This year has been defined by a run of heat waves that, taken individually, might have looked like isolated, unfortunate events. In March, the American Southwest endured a heat wave months earlier than the region would typically brace for that kind of severe heat. Around the 4th of July, the northeastern United States, a region without the deep infrastructure and public preparedness the Southwest has built up over decades of dealing with genuine summer extremes, found itself trapped under its own brutal stretch of heat. And across June and July, Europe suffered conditions severe enough that by the time August arrived, the continent was actively battling record-setting forest fires, the delayed, smoldering aftermath of weeks of accumulated heat and drying vegetation. Atmospherics. Scientists studying each of these events individually kept finding the same signature underneath all three. A stubborn, slow-moving atmospheric configuration called an omega block, a high-pressure ridge flanked by 2 low-pressure troughs, locking heat in place for weeks at a time across 3 completely different regions of the planet. Here's the mechanism behind why that specific pattern has become so common, and it traces back to something scientists call Arctic amplification. The Arctic has been warming considerably faster than the rest of the planet for years, and that disproportionate warming has been steadily narrowing the temperature gap between the Arctic and the tropics, the exact gap that gives the jet stream its speed and its structure. As that gap shrinks, the jet stream slows, and a slower jet stream stops moving in a relatively straight, efficient line, and instead begins meandering, forming large wave-like dips and bulges that, when they grow large enough and, critically, stop moving, lock into place as blocking patterns. That's the broader story behind 2026's run of heat waves, and it's a story scientists have been tracking with increasing confidence for years now, well-supported, well-documented, consistent with the northward migration Osman's team predicted back in 2021, but buried within that broader, well-understood story was a specific detail that didn't fit. A new study, led by researcher Sheng and collaborators, focused specifically on the summer North Atlantic jet, the exacto segment of the jet stream sitting directly over one of this year's hardest hit regions, and found something that ran directly against the expected trend. Rather than drifting northward the way the broader Arctic amplification story predicted, the summer North Atlantic jet had recently shifted equatorward, southward toward the tropics. moving in precisely the opposite direction from what over 1,000 years of ice core reconstruction and climate modeling had suggested it should. I want you to genuinely sit with how strange that is, because it's the heart of this entire mystery. Nearly every major atmospheric circulation pattern researchers track is expected to shift poleward as the planet warms, a consistent, well-documented signature of a warming climate system reorganizing itself. Osmond's ice core reconstruction had specifically flagged the North Atlantic jet as a case study for exactly that expected northward migration. And now, in the very years that migration was supposed to become increasingly apparent, the summer version of that same jet stream segment was caught moving the wrong way entirely. So the investigation shifted. If the jet wasn't behaving the way the dominant theory predicted, something else had to be driving it, some factor powerful enough to override, at least temporarily, the broader warming-driven trend everyone had been expecting. Researchers traced the answer to something with a genuinely evocative name, the North Atlantic warming hole, a strange, persistent patch of ocean that has been doing something almost nothing else on the planet is doing, staying stubbornly cool, or at best, warming considerably slower than the ocean surrounding it, even as global temperatures climb virtually everywhere else. That unusual, localized ocean temperature anomaly turns out to alter the thermal structure of the atmosphere, sitting directly above it, and researchers found that alteration was specifically capable of pushing the summer North Atlantic jet toward the equator, directly, counteracting the broader poleward pull driven by Arctic amplification everywhere else. Here's where the mystery deepens rather than resolves, because the researchers behind this specific study attribute the shift primarily to internal climate variability, meaning natural cyclical fluctuations within the climate system itself, rather than a direct consequence of human greenhouse gas emissions. That's a genuinely important, almost counterintuitive finding. In the middle of a summer this hot, this widely disrupted by extreme heat, the specific southward nudge currently pulling on the summer North Atlantic jet isn't, at least according to current evidence, humanity's fingerprint directly. It's something closer to the climate system's own internal noise, a natural wobble large enough to temporarily mask, or even reverse, the broader warming-driven trend playing out everywhere else in the jet stream's behavior. And yet, the researchers are clear that this is very likely a temporary reprieve from the broader trend, rather than a permanent contradiction of it. Their models suggest human-driven warming is expected to become the dominant factor reshaping this specific piece of the jet stream by around the 2050s, meaning the natural variability currently in the driver's seat is, on a long enough timeline, expected to eventually get overtaken by the same force reshaping everything else. There's a second thread in this mystery worth following, because it connects this jet stream puzzle to an entirely separate, equally significant area of ongoing climate research. That North Atlantic warming hole, the strange, stubbornly cool patch of ocean behind this southward jet shift, is widely understood by researchers to be at least partially connected to a weakening in the Atlantic meridional overturning circulation, the vast ocean conveyor belt responsible for carrying warm water northward through the Atlantic and playing a central role in regulating climate across both North America and Europe. A slower overturning circulation moves less warm water into that specific stretch of ocean, which helps explain why it's remained cool while the water surrounding it has warmed considerably. That means the same broader weakening in Atlantic Ocean circulation, already the subject of serious, separate scientific concern about long-term climate tipping points, maybe quietly reaching out and reshaping the exact jet stream pattern responsible for pulling heat into unexpected places this year. A genuinely unsettling example of how interconnected different pieces of the climate system turn out to be once researchers trace the causal threads back far enough. So where does that leave the mystery in the end? Two separate mechanisms operating simultaneously on the same general region during the same general season, pulling in genuinely different directions. Arctic amplification, slowing the broader jet stream and generating the persistent wave-likes, blocking patterns behind this year's run of omega block heat waves, a well-established, directly human-driven process. And layered on top of that, a specific, recent, unexpected southward tug on the summer North Atlantic jet specifically, driven for now by natural variability, interacting with a stubborn, unusual patch of cool ocean water that may itself be tangled up with a weakening Atlantic circulation system. Not one single villain behind this year's heat. Two separate forces discovered through two separate lines of evidence, converging on the same summer, the same headlines, the same string of heat waves that felt, to anyone living through them, distinctly unlike the heat waves of years past. That's genuinely the most fascinating part of this entire investigation, I think. It would have been simpler, and in some ways more satisfying, if scientists had found one clean, singular explanation, one villain to point to and say, This is why 2026 felt different. Instead, the deeper they looked, the more the story split into multiple interacting threads, a slowing jet stream here, an unexpected reversal there, an ocean current possibly tying the two together beneath the surface, evidence gathered from ice 1,000 years old converging, with evidence gathered from data collected just this year. That's what real scientific investigation actually looks like. Not a single dramatic reveal, but a slow, patient accumulation of evidence that keeps complicating the picture, even as it sharpens the underlying truth. If you lived through any of this year's heat waves, the Southwest's unusually early spring event, the Northeast's brutal stretch around Independence Day, or Europe's prolonged June and July ordeal that's still smoldering into August through record wildfires, you were living through the visible surface of exactly this deeper, still unfolding scientific mystery. Atmospheric forces shifting in ways researchers are only now beginning to fully untangle, playing out invisibly, miles above your head, while the heat itself made the consequences impossible to ignore at ground level. I'll be watching closely for whatever comes next in this investigation, particularly any follow-up research that either confirms or complicates the Sheng team's findings on the North Atlantic jet's southward shift, and any further evidence connecting that shift more directly to the broader questions swirling around Atlantic circulation weakening. This is exactly the kind of story that tends to keep evolving well after the initial discovery, as other research groups work to test, confirm, or refine what's currently being reported. Subscribe so you don't miss that follow-up, and drop a comment below with your own experience of this year's heat, wherever in the world you happen to be living through it. I read every one of these, and a mystery playing out on a scale this large genuinely benefits from hearing how differently it landed, depending on where you were standing when it happened. Stay curious about the invisible forces shaping the world above your head, because sometimes the most important discoveries in climate science aren't the ones that confirm what we already expected. They're the ones that quietly, stubbornly refuse to. I will see you in the next one.